Hello and welcome to this video in which we show how to do the convolution of a unit step function with a decaying exponential function. To motivate this problem, I've drawn a block diagram of a system. The system itself has an impulse response h of t. I've drawn or graphed this impulse response here. You can see it's a decaying exponential, and for values of t less than 0, it has a value of 0. The input to the system is the unit step function, u of t. And the unit step function is 0 until t gets to 0, and then it's 1. And our goal is to compute the output of this system in response to this unit step. The output is the impulse response h convolved with the input u of t. As an aside, this is actually a fairly realistic example in the sense that many RC circuits, which I use often as low-pass filters, have impulse responses that look like this, and quite often I'm interested in the response of a circuit when a voltage changes abruptly from 0 up to some value. So let's see then if we can compute this convolution. I've written out the convolution integral here. And before we actually work the convolution integral, we need to talk a little bit about what this means and what's going on. My experience has been in teaching this, if we don't talk about it now, you'll need to talk about it later, and by then you'll be angry and confused. This notation here represents the convolution of h and u. And this notation is actually bad. It's awful. The reason for that is that it gives the impression that I take h at some particular point in time t and u at some particular point in time t, and by convolving them I end up with y at some particular point in time t. And that's just not the way it works. In order to get y at some time t, I actually have to look at all of h, where in principle this might be from minus infinity, the infinite past, through the infinite future. I also have to look at all of u. So again, this may be from the infinite past to the infinite future. So to get the output at a given time t, I have to look at the entire length of h and the entire length of u. And the way we do that mathematically is by using tau. Tau here is a dummy variable of integration, and tau will go from minus infinity to infinity. We'll look at the entire length of h and the entire length of u. So with that understanding, we can now turn our attention to working the integral. The first thing we want to do is draw h and u. This helps you understand what's going on, and it helps you set up the limits of the integral. Okay, so h of tau looks like this. It's a decaying exponential, and when it's non-zero, it's e to the minus a tau. For values of tau less than 0, it's 0. U of t minus tau is a little bit more complicated. The fact that I have a minus tau here means that my u is going to be flipped about the point tau is equal to 0. And then the t and the minus tau actually end up shifting u of tau to the right by t. So if this is the value that I have of t if I've chosen this particular value of t, then u of t minus tau is going to look like this. And it makes the transition from 1 to 0 at this value of t. So in order to work the integral, I need the product of h of tau and u of t minus tau. So let's draw what that product will look like. First, I look at values of tau less than 0. And when tau is less than 0, h of tau is 0. So I have 0 times 1. The product of 0 and 1 will be 0. For values of tau greater than t, I have that u of t minus tau is 0. And so the product again of h of tau and u of t minus tau will also be 0. For values of tau between 0 and t, I have u of t minus tau, which is 1, times h of tau, which is this e to the minus a tau. So for values of tau between 0 and 1, I have something that looks like this. It's equal to e to the minus a tau. So again, this is the product of h of tau and u of t minus tau. And it is non-zero between 0 and t. So to compute the integral, what I need to do is find the area under this product. And I can do that, again, conceptually, this is what computing the integral does. And I can do this by just working out the integral. So let's write out what this integral should be. It's the integral from 0 to t, e to the minus a tau d tau. Since I'm integrating an exponential, I'll end up with a 1 over the constant in the exponential. In this case, that constant is minus a. Then e to the minus a tau evaluated between 0 and t. And so the 1 over minus a stays. The upper limit t gets plugged in for tau, and I have e to the minus a t. The lower limit, 0, gets plugged in for tau, and I have e to the minus a 0, and that e to the anything times 0 is 1. Okay, so I can rewrite this as 1 over a 1 minus e to the minus at. You'll notice that this is now a function of t. This is our y of t, which is h of t convolved with u of t. When I graph it, it looks something like this. We call this sometimes an asymptotically increasing exponential. It's asymptotically approaching the value 1 over a. So this is y of t. Okay, so that wasn't bad at all. One thing that we need to do before we're done, our picture here assumes that t is greater than 0. If t were less than 0, then I would have a picture that looks like this. I would have u of t minus tau looking like this, and everywhere that u of t minus tau is non-zero, which is out here, h of tau would be 0. Everywhere that h of tau is non-zero, which is here, u of t minus tau would be 0. So when t is less than 0, I have the situation that the product of h of tau and u of t minus tau is always 0, which means that the integral will always be 0. I can complete this y of t, or the convolution, is equal to 1 over a 1 minus e to the minus at when t is greater than 0, and 0 when t is less than 0. So we've computed the convolution of h of t with u of t. The last thing I'd like to do before ending the video is show that the convolution does not depend on the order in which we have the signals. I've written y of t is u of t convolved with h of t. So the order of the two signals is now interchanged. And if I work out the integral, write down the integral, I have this is the integral of u of t h of t minus tau d tau. So as we did before, we draw out the signals, and we'll take their product, and then we'll work that integral. U of tau is very simple. It's just the unit step function. H of t minus tau is my decaying exponential. So I've flipped it about the point tau is equal to 0 so that it now is the opposite direction as what we were used to or what we had before, and then shifted it to the right by t. And we'll again assume for these pictures that t is greater than 0. So now I need to get the product of the two. And for values of tau where u of tau is 0, the product will be 0. For values of tau where h of t minus tau is 0, up here, the product will be 0. And for other values of tau, I get the product looking something like this. So where the product is non-zero, the value for the product is going to be u of tau, which is 1, times h of t minus tau, which is e to the minus a t minus tau. And again, my goal is to find the area under this curve by working the integral. The first thing to do is to multiply this out. And so we have minus a t plus a tau. Now we can write this as e to the minus at, e to the a tau, and again we're integrating from 0 to t with respect to tau. E to the minus at, t is a constant with respect to tau, which we're integrating over. So I can take this chunk and move it outside of the integral to get e to the minus at, the integral from 0 to t, e to the a tau d tau. And so I just need to work this integral. This will be 1 over a e to the a tau evaluated between 0 and t. So if I plug t in for tau, I get 1 over a e to the at. If I plug 0 in for tau, I'll have minus e to the a0, and this is 1. Okay, now I still need to take this guy and multiply these guys together. So when I do that, I have 1 over a e to the minus at, that's this guy here, times e to the at minus 1. And when I multiply these guys out, I end up with 1 over a 1 minus e to the minus at, which is exactly what we had before. So if you were worried that the math wasn't going to work out, you don't need to worry anymore. It all works out beautifully. And with that, I think we'll end this example. Thanks for watching.